Welcome to Tech Disruptions, deep dives into the technologies reshaping industries, from AI to quantum to biotech. Let's get into it.
Quantum computing, for years, has been presented as this almost mythical technology, poised to unlock incredible breakthroughs. But the latest conversations suggest something different, a death of early hype. What does that even mean for an industry that hasn't quite delivered on its biggest promises yet?
It means the industry is moving past the breathless predictions of quantum computers solving world hunger next Tuesday. The initial wave of optimism, fueled by big claims and abstract potential, is giving way to a more pragmatic, even cautious, assessment of what is achievable and when. It's a reality check, not necessarily a death sentence for the technology itself.
A reality check, but also a $10 billion question hanging over the industry. That's a huge amount of investment. Is this death of hype a sign that some of that money is about to dry up, or that expectations are simply realigning with the actual physics?
It's more of a realignment. The early money was often speculative, betting on a future that felt almost science fiction. Now, the investments are becoming more strategic, more focused on engineering challenges and specific achievable milestones rather than just raw qubit counts. It's a sign of maturation, albeit a painful one for some of the earlier, less grounded ventures.
So instead of a quantum winter, are we looking at a quantum spring cleaning of sorts?
That's a good analogy. It's less about a freeze and more about clearing out the underbrush of unrealistic expectations. It forces companies and researchers to define concrete problems, demonstrate incremental progress, and justify the immense capital expenditure with tangible steps, rather than just abstract potential.
And speaking of concrete steps, IBM has set a very specific, very ambitious target, a 4,000 qubit machine by 2029. On the surface, that sounds like a massive leap, but what's the actual significance of that number? 4,000 qubits sounds impressive, but are all qubits created equal?
Not at all. That's precisely where the death of early hype comes in. Raw qubit count is a bit like judging a supercomputer solely by the number of transistors on its chips without considering how those transistors are connected, how efficiently they operate, or how coherent they are. The crucial metric for a quantum computer isn't just the sheer number of qubits, but their quality.
So what makes a qubit high quality?
It comes down to factors like coherence time, how long a qubit can maintain its quantum state before decohering and losing its information, and error rates, which are incredibly high in current machines. A 4,000 qubit machine with high error rates and short coherence times isn't necessarily more powerful than a 100 qubit machine with much better performance metrics. It's the effective number of reliable, entangled qubits that really matters for solving complex problems, not just the physical count.
So IBM's 2029 target is less about a raw number and more about signaling an engineering roadmap. It's saying, we believe we can build a machine of this scale, and here's the path.
Exactly. It's a statement of intent and a challenge to their own engineering teams. It also puts pressure on competitors. However, the path to useful quantum computation involves far more than just scaling up qubit numbers. It requires breakthroughs in error correction, which is arguably the biggest hurdle. Without robust error correction, adding more physical qubits just adds more noise. It's like trying to have a conversation in a stadium with 4,000 people shouting at once.
This leads to the concept of fault-tolerant quantum computing. That's the holy grail, right? A machine that can actually perform complex calculations without being overwhelmed by errors. How close is the industry to that, and how does a 4,000 qubit machine by 2029 fit into that picture?
Fault tolerance is indeed the holy grail. It's the point where quantum computers could theoretically tackle problems classical supercomputers can't. The challenge is that current estimates suggest that achieving a single logical qubit, a single error-corrected qubit, might require hundreds or even thousands of physical qubits. So a 4,000 qubit machine by 2029, even if successful, might only yield a handful of functional logical qubits. It's a significant step, but not yet the leap to universally fault-tolerant problem-solving machines.
That's a critical distinction. So even if IBM hits that 4,000 physical qubit target, the industry is still potentially years, if not decades away from the kind of truly transformative applications that were hyped early on.
Precisely. The goal isn't just a larger quantum processor, it's a reliable quantum processor. The industry is still in the noisy intermediate scale quantum, or NISQ era. IBM's target is pushing the boundaries of NISQ, but the transition to fault tolerance is a qualitative, not just quantitative leap. It's about fundamentally changing how errors are handled, not just having more unreliable components.
This all sounds like a very expensive endeavor. The $10 billion question in the title refers to this massive investment. Who's paying for this, and what are they expecting to get out of it, given these long timelines and technical hurdles?
Governments, primarily the US and China, are significant funders, viewing quantum computing as a strategic national interest akin to the space race or AI development. Major tech companies like IBM, Google, Microsoft, and Amazon are investing heavily, seeing it as a long-term play for competitive advantage, even if the returns are decades away. And then there's venture capital, which has poured money into startups, often with the expectation of faster breakthroughs than the physics currently allows.
So, some of that venture capital might be feeling the pinch of this death of early hype.
Absolutely. Early-stage quantum startups that raised capital based on ambitious roadmaps and pure potential are now under pressure to show more tangible progress or at least a clearer path to commercial viability. The market is getting tougher for those without a very focused niche or a demonstrated ability to overcome engineering challenges. It's part of that spring cleaning mentioned earlier.
Beyond the technological challenges and the shifting investment landscape, there's a significant geopolitical dimension emerging, particularly with China. The source mentions China's exports. What exactly is happening there, and why is it so strategically important?
This is a critical development. China has emerged as a major player in quantum technology, not just in research, but in the supply chain for critical components. The recent move by China to restrict exports of certain quantum-related materials, specifically high-purity germanium and gallium nitride, underscores this.
Why those specific materials? What are they used for in quantum computing?
Germanium is crucial for superconducting qubits and for certain types of quantum sensors, while gallium nitride is vital for advanced semiconductors, including those used in quantum control systems. By restricting their export, China is effectively tightening its grip on key parts of the global quantum supply chain. It's a strategic maneuver, mirroring earlier restrictions on rare earths, which are essential for many high-tech industries.
So, if you're a quantum lab in the US or Europe and you rely on these materials, China's export controls could directly impede your progress?
Precisely. It creates a vulnerability. For countries and companies not based in China, it means either scrambling to find alternative suppliers, which might not exist or be able to meet demand, or investing heavily in domestic production of these materials, which is a long and costly process. It slows down research, increases costs, and can force a reevaluation of national quantum strategies.
This isn't just about economic leverage. It sounds like a national security concern. If one nation can control access to the fundamental building blocks of future computing, that's a powerful position.
It's absolutely a national security concern. Quantum computing has implications for cryptography, material science, drug discovery, and artificial intelligence, all areas with direct military and economic applications. Controlling the raw materials translates into significant geopolitical influence and can dictate the pace of quantum development globally. It forces other nations to de-risk their supply chains and potentially decouple from Chinese sources, even if it means slower progress in the short term.
This sounds like a race, but a highly constrained one due to these supply chain bottlenecks. Is the rest of the world prepared for this kind of strategic competition over quantum components?
Many countries are certainly aware, but preparedness varies. The US, for example, has recognized the need to secure critical supply chains across various advanced technologies, including quantum. Europe is also investing in its own capabilities. However, these are long-term strategies. In the immediate future, these export controls present a significant hurdle that the quantum industry must navigate. It adds another layer of complexity to an already incredibly challenging technical field.
So we have the technical hurdles of building a truly fault-tolerant machine, the financial pressures of maturing expectations, and now geopolitical jockeying over raw materials. It's a much more complex picture than the early hype suggested.
Far more complex. The initial narrative was often about a singular, almost inevitable technological breakthrough. The reality is a multifaceted challenge involving physics, engineering, economics, and international relations. It's a marathon, not a sprint, and the terrain is proving to be much rockier than anticipated.
Given all these factors, what are the most realistic near-term applications we can expect from quantum computing, even with the limitations of the NISQ era? Where might we see the first genuine impact?
The focus is shifting to highly specialized applications where even noisy quantum machines can offer an advantage over classical systems. These include areas like material science simulation, specifically designing new catalysts or battery materials, where quantum mechanics plays a fundamental role. Also, certain optimization problems in logistics or finance, where small gains can yield massive returns.
So, not cracking every encryption algorithm overnight, but perhaps designing a better solar panel or optimizing a shipping route by a fraction of a percent?
Exactly. Think niche, high-value problems rather than broad, general-purpose computation. Drug discovery is another area, simulating molecular interactions that are too complex for classical computers. These are applications where even a partial quantum advantage can be hugely impactful. But even these are still largely in the research and development phase, requiring significant breakthroughs in algorithm design and hardware stability.
It seems like the industry is collectively moving from asking, can we build a quantum computer, to what can a noisy, imperfect quantum computer actually do right now?
That's the core shift. It's about finding the quantum sweet spot, problems that are hard for classical computers, but not so hard that they require perfectly fault-tolerant quantum machines. It's a much more grounded approach, acknowledging the limitations while still pushing the boundaries of what's possible with current and near-future hardware.
So if someone is listening and trying to make sense of quantum computing today, what are the big takeaways? What should they understand about where this technology stands?
First, the quantum computing landscape has matured beyond initial hype. Expectation management is key. The industry is in an engineering phase, focusing on incremental, hard-won progress, not magic bullet solutions.
And second?
The industry is moving towards specific, niche applications in areas like materials science and optimization, rather than general-purpose computing. The truly transformative applications are still some ways off, awaiting fault-tolerant machines.
And the third key insight?
Geopolitical competition, particularly over critical materials, is now a major factor. Supply chain security and national self-sufficiency in quantum components are becoming as important as the technological breakthroughs themselves.
It feels like the industry is settling in for a long, hard climb rather than expecting a sudden ascent.
That's a fair assessment. The path to truly impactful quantum computing is proving to be longer and more challenging than many initially anticipated. But the fundamental promise of the technology remains compelling enough to justify the continued investment and effort.
Thinking about that long climb, what are the big questions that remain unanswered right now?
One big question is whether the current qubit architectures will be the ones that ultimately scale to fault tolerance, or if the field is still waiting for a fundamentally new approach.
And another?
How will the global supply chain for critical quantum components evolve under increasing geopolitical pressure? Will there be genuine self-sufficiency in key regions, or a continued reliance that becomes a point of vulnerability?
That's all for this episode of Tech Disruptions. Join us next time as we keep exploring the technologies reshaping our world. Thanks for listening. We'll see you next time.
Stay curious out there.